Welcome to lecture 15. We were discussing well stirred reactor yesterday in lecture 14, and these are the equations that we had. So, remember that this is now a vessel in which there can be one input stream or there can be multiple input streams, and they are carrying fuel and oxidizer typically, and then the fuel and oxidizer react inside the chamber. The products are formed, temperature is raised to some higher value, and then the products at that higher temperature and a different composition, chemical composition will exit. So, there is an exit stream, and we said that it is a well stirred reactor. So, the mixing is extremely good, perfect in fact, and also at various physical locations inside the well stirred reactor you will have the same concentration, and you will also have the same reaction rate, you will have the same temperature, and all these are the same as what you get at the outlet. So, we discussed this quite a bit last time, and we also identified that what we are trying to do is actually trying to get the outlet stream. We are trying to determine the outlet stream temperature and the composition, that means the concentrations of various species in the outlet stream. That is our purpose, and for that purpose we understand that there must be n plus 1 variables. One is temperature, and then there are n species concentrations. So, n plus 1 variables, and for those n plus 1 variables we need equations, and we already developed those equations, and those equations are one for energy, which will relate to temperature, and then there are n species equations. So, we developed all this in the last class, and we also understood that these are not differential equations. These are algebraic equations which are coupled to one another, and they have non-linearities in them. We also understand that these equations that we developed were for steady state. So, there is no variation with time. So, it does not, the set of equations will not require a set of initial conditions. So, we will solve these, and we also understood yesterday that solving this may not be possible in class because these are coupled equations with non-linearities in them. So, we are just describing the overall scheme of things, and in that context we started in fact looking at an example problem. So, we were looking at this example 6.2 from Stephen Turns's book, which is about determining the blowout characteristics of a reactor which is 80 millimeter diameter, and it had ethane air stream entering at 298 Kelvin. So, the fuel is ethane, the oxidizer is air, they are entering at 298 Kelvin. And for this particular problem we will not deal with large number of species, we will try to keep the number of species as low as possible, and as low as possible means 3 as we discussed. So, the simplest model is taking fuel plus oxidizer giving you products. When I write PR products, I am not distinguishing between CO2 and CO or CO2 and H2 and all that. So, products is product, there is no specific name given to a particular species. Okay. That is the greatest level of simplification that we can possibly use. So, we need to solve these equations, and for the species equation I had written something like this yesterday, lecture 14. This is what we did. So, this comes from the species equation. So, the species equation, of course, as we know from here, the work done previously, is that it will have a species production term which is omega dot I into molecular weight of the ith species into volume plus m dot I in minus m dot I out. Again, recall what the notations are. M dot I in is the rate of inflow of the ith species into your control volume, which is the well stirred reactor inside volume. And we also wrote that we wrote m dot I as m dot, that is the overall mass flow rate, multiplied by yi in. So, at the inlet, what is the mass fraction of the ith species? That is yi in. that quantity is yi n. So, we did this and this is used here, this is used here, and that I wrote in the last class. So, you can compare the two and see that okay, this is identifiable, this is actually this stuff, all right. So, what you see here is the species equation written for fuel. So, this term goes in here and instead of y I am writing y f. So, that is easy, and then we had this omega dot I w I into volume. So, you can see there is a w f and there you can also see there is a volume. So, whatever else you see here, all this must be coming from the omega dot I. Okay.
What is this F1?
F1. Which one? F in actually.
No, F1. F1 equal.
Oh, okay, small f1, right. So, the question is what is small f1? F1 is just a function. We see if you, the species equation is actually this, right. So, this function, this expression is written as or can be also thought of as f1 equal to 0. That is it, just a shorthand notation, that is all, f1 equal to 0. Okay. So, this thing in blue is in fact omega dot I, and this is something which we did not discuss much in lecture 14. So, I had written little bit on this. So, the omega dot I will, as I mentioned last time, omega dot I will come from a one step model, because we are assuming one step reaction, and omega dot I is 1 over volume dNI dt by definition. So, we did this quite some time back, and this is a well stirred reactor, volume is not changing. So, we are, this is a rigid vessel. So, it is here, it is the volume can come inside and we can write d dt of concentration of x I. So, for omega dot fuel it becomes d dt of concentration of fuel. Now, the next job is to bring in the model that we are proposing. We are proposing to use a single step model for all this, and we want to bring in the single step model here to, so that we are able to write d dt of concentration of F. Now, d dt of concentration of F in our context means d dt of concentration of C2H6 quite obviously, and that is equal to minus Kg into C2H6 to the power m and O2 oxygen to the power n. Okay. So, this is the global reaction rate constant, and this Kg expression is given in the textbook. So, that is there in chapter 5, table 5.1. So, this is the global reaction rate constant. We have to go to table 5.1 and then pick up the various parameters associated with Kg. Now, what is Kg? Kg is, of course, Kg is A exponential minus E over R bar temperature. Remember, the reaction rate constant does not have concentrations explicitly in that. Okay. So, it is just the pre-exponential factor into exponential minus E over R bar T. Now, you go to table, if you go to table 5.1, then we will know that it gives us this quantity, it calls it a TA, and the TA is, how much is this? Wrote it yesterday, isn't it? 15098. So, this is 15098 Kelvin. So, that is easy, so that you have here. from the table. Now, for A, the value given is 1.1 10 to the power 12 gram mole per centimeter cubed to the power 1 minus m minus n, and this is per unit time. So, why is it in gram mole? Because that's what is used in that particular table, but we don't like gram mole and centimeter cube here because we are using SI units. So, we will convert this to kilomole and cubic meter. Okay. So, if you look up table 5.1, it will give you 1.1 in 10 to the power 12 in this unit. Okay. So, the table uses gram mole per centimeter cube, that is the only reason I am writing it here. Now, if we want to convert this, one, then what do we have to do? So, gram mole per centimeter cube to the power 1 minus m minus n is also 10 to the power minus 3 kilomole right. So, that is 1000, because 10 to the power minus 3 10 to the power minus 6, that will give you 1000 to the power 1 minus m minus n kilomole per meter cubed to the power 1 minus m minus n. Okay. So, we also wrote m and n yesterday. Remember what those are? The values are m is 0.1, n is 1.65. So, if you use these, then this gram mole per centimeter cubed can be converted in terms of kilomole per meter cubed. And if you do all that, then it is possible to show that kg is 6.19 in 10 to the power 19, 10 to the power 9, sorry, exponential minus 15098 divided by t. Okay. So, where did this 6.19 into 10 to the power 9 come from? That is from that this. Okay. That is this contribution, because okay, this and 1.1 into 10 to the power 12 together will give you that 6.19 10 to the power 9. Okay. Are you comfortable with this, or you want to check this out quickly? If you have a calculator, you want to check this out? We have to do this quickly. So, what is 1000 to the power 1 minus m minus n? M plus n is 1.75. So, 1 minus m minus n is minus 0.75. So, 1000 to the power 5.6, 1000 to the power minus 0.75 is 5.62, and that multiplied by 1.1 will be 6.19, and that is how we got this. Okay. So, this should be fine. So, this is kg. If you still have doubts, you have to work this out yourself. Okay. You have to do this at home. Now, we were writing this expression for omega dot f, and omega dot f is minus kg C2H6 to the power m and O2 to the power n. So, it is minus 6.19 10 to the power 9 exponential we have all this. So, yesterday there was a question on what is the unit of kg. So, what I mentioned yesterday, I would like to repeat today also that omega, you check the unit of omega dot f first. Omega dot f is of course the same as omega dot f is same as d concentration of f dt. We just did that today. So, what is the unit of this?
Kilomole per meter cube per second.
Kilomole per meter cube second. Kilomole per meter cube second. So, the unit of this should be such that when multiplied by these units of these, it should be able to give you kilomole per meter cube second. Okay. So, again I think this is not hard for you to check out. So, this is the expression for omega dot f. What were we discussing few minutes back? We were discussing species equation. We are discussing species equation. We are trying to get the species equation for fuel. So, this is what we had. Species equation for fuel, correct. We said that this term is easy. We said that this Wf and volume we understand, correct. So, the difficulty was here. Now, of course, we understand that there has to be a kg, right, because kg into concentrations raised to some powers multiplied, that is what will give this term. Now, do we understand this 1.75 now? Power 1.75, 1.75 must be m plus n. Okay. Now, the question that you will have in your mind is, okay, how does the pressure by R bar T term come here? Okay. So, that is a valid question. What do you think happened here? Why did P by R bar T term come? Yeah, so we understand that when we writing omega dot f, in the basic form it is written in terms of the concentrations, not mass fractions, but concentration of xi, let us say, must be this. Correct. Again, this is something which probably I did not do directly, but looking at this, does it appear reasonable to you? So, what does it do? What does this expression do? It expresses the mole fraction in terms of a mass fraction. So, this connects the mole fraction and the mass fraction. And how can we do this? Using ideal gas law. Okay. So, let me just write this as a homework, in the sense that you take for granted. After the class, check this out yourself. Can you derive this? Okay. As of now, let us take this for granted. So, you are clear about this omega dot f, this expression up to here, all right. Up to this is fine. So, in this expression, we will replace concentrations in terms of mass fractions using this sort of a relation. Why are we doing this? Because the well-starred reactor model that we built was in terms of the mass fractions. So, we wrote yi in, yi out and all that. And the species equation has all mass fractions, the way we formulated it yesterday. That is why we want to get rid of the concentrations and bring the mass fractions. Okay. So, if you do that, then we will get this also. So, now we understand that P by R bar T must have come from the conversion of concentrations to mass fractions, correct. You understand that 1.75 must be m plus n, and this 0.1 is m and 1.65 is n. Okay. There is another small thing that we want to check out, like for example, here there was a W mix. So, W mix is a mixture molecular weight. So, the mixture molecular weight was used to convert mass fractions to mole fractions, right. So, the mixture molecular weight appears in the expression which connects mole concentrations, not mole fractions, sorry, which connects concentrations to mass fractions. Okay. Now, that mixture molecular weight does not seem to appear here. So, it must have gone somewhere, right. So, the mixture molecular weight has been expressed in this equation. Mixture molecular weight has been expressed in terms of individual mass fractions. How? Okay. If we want to say mixture molecular weight, then that is m times summation n I . Okay. What is n I? Number of moles of the ith species. So, if you sum them up, you get the total number of moles in the mixture. So, mass of the mixture, this m is actually m mixture, right. So, if you divide the mass of the mixture by the total number of moles, then you will get the molecular weight of the mixture. Okay. And this is m. So, can this be, can W mix be written in terms of the mass fractions of individual species? Can it be done? Okay. So, the way to do it is, instead of n I, we will write m I by W I, correct. N I is the number of moles of the ith species. So, that must be mass of the ith species divided by the molecular weight of the ith species. Mass by molecular weight is the number of moles, is not it. So, this is kg divided by kg per kilomole of the ith species. So, that gives you kilomole of the ith species. Okay. So, this is simple. Now, we will divide both the numerator and denominator by m mixture. So, it will become 1 here, and this will become m I divided by m mixture divided by W I. So, this is 1 divided by y I by W I. So, this is W mixture, correct. So, this is what has been used in this expression. Okay. Just to revise, we understand that this should be there in the fuel species equation, no problem with this, correct. And there is also no problem with this molecular weight of the fuel and the volume of the chamber. So, no problem with that. We understand that there has to be a kg also. So, all this that you see here is primarily because you are converting concentrations to mass fractions. In the process, you got a mixture molecular weight and you wanted to replace that also. So, that is why this thing, the sum of these is actually the mixture molecule weight, that has come into picture. Okay. There is just one little thing that we have not said so far, that is this 0.233 into YOX, where does this come from? So, this YF by WF is easy, because this must be from the fuel concentration. Okay. Now, here you should similarly have YO2 by WO2. Okay. But instead of that, what we are doing is we are writing Y oxidizer divided by W oxidizer. Now, oxidizer is the whole thing, it can be air, in our case it is air. So, it has oxygen and nitrogen, and we are multiplying this by 0.233 to actually get the mass fraction of oxygen, because air has 23.3% by mass of O2. So, that is the only change. So, we have this now, we have this whole thing here. So, we call this F1. So, this is the fuel species equation. Now, let us see what else we can do. We can, of course, just as we have done a fuel species equation, we can also do an oxidizer equation. So, there is a fuel equation which we called as F1, and there can be also an oxidizer equation which is F2. Again, it will look clumsy if I write this F2 equation, but it will be exactly in similar lines with the last one. Okay. So, instead of omega dot fuel, we have to use omega dot O2, and for that omega dot oxidizer, for that we will use an air fuel ratio. So, the oxidizer equation, apart from the usual terms, will have an air fuel ratio multiplying omega dot F. Okay. So, this is the oxidizer equation. Then there will also use a product equation, but we will not directly use a product equation. We will just say YF plus Y oxidizer plus Y product equal to 1. So, that will be fine. We do not need to use a separate equation for products. So, that is a third equation. How many unknowns do we have here? 3 plus 1, isn't it? So, this is fuel, oxidizer, products, and temperature. So, the fourth equation is in fact the energy equation. So, energy equation will be F4 equal to 0. How do you write the energy equation? Very simple. We have you have seen the energy equation before. So, the energy equation is so we have this, and as F4 we will write things like this. I think it's not very important for you to copy this, because this is also available as part of example 6.2 in the book. So, I would in fact suggest that you do not write this, you just take a look at this. This is available to you in the book. So, there is no point writing it. Let us just see what has been done. This is YF. YF means YF in the outlet stream. If I write YF in, that means it is the inlet stream. If I do not write anything, if I just write YF, then that means it is a mass fraction within the control volume or going outside through the outlet stream, both are the same. And we are writing YF into within brackets enthalpy of formation of the fuel plus Cp times T minus T ref. Okay. So, we have actually used a simple model for Cp. We have assumed that Cp to be constant. So, that I mentioned yesterday that in this problem we are considering all Cp's to be the same and also considering all Cp's to be constant, so not changing with temperature. So, if Cp is not changing with temperature, integral Cp dt is Cp into T minus T ref. T ref is the reference temperature. So, we have that, and in the expression you see that there are 3 terms which are positive and then there are 2 terms which are negative. Okay. So, the 3 positive terms correspond to the outlet stream, because in the outlet you have fuel, oxidizer and products, right, and the inlet stream there is fuel coming in and there is also oxidizer coming in. Okay. So, this should be okay. So, what I suggest is that do not write this down, there is no need, but keep this in mind that you have to go to example 6.2 and look at all these terms carefully. So, again fuel equation, oxidizer equation, sum of species equal to 1 and the energy equation, all right. So, we will try to solve all this, and if we solve all this, then we can in fact solve for the reactor problem. Since you have seen so many equations, maybe it is good time to also remind you as to what problem we are trying to solve. We are trying to solve this, no? We are sending in some inlet streams, actually in this example problem just one inlet stream, and something is going out. So, we are trying to solve these equations and get all the concentrations and the temperature, but remember the problem statement says that we are interested in the blowout characteristics of the well starred reactor. Okay. So, an 80 millimeter diameter spherical chamber where we are sending ethane and air, and we want to see what are the blowout characteristics. So, what are blowout characteristics? So, if you have this mixture going into this reactor, it is designed in such a way that it is very well mixed, then you are sending this m dot, same m dot will go out, and we expect that reaction will take place here. Fuel will react with the oxidizer to give you products. But will it always react? Okay. If you start with a small value of m dot, so we are talking about solving these equations multiple times. So, think of solving all these equations, all these 4 equations first with a small value of m dot. With small value of m dot, that is slow flow going into this, we expect reactions to take place, and the fuel and the oxidizer will get consumed and then products will go out. And then start thinking of doing the same thing for a little larger value of m dot. So, we increase m dot and do the same process, and maybe there is still reaction taking place. But if you indefinitely keep on increasing m dot, there will be a time when there will be no reaction here. Okay. So, what is happening there? That is called blowout, that you are sending this fuel air mixture at a high speed and they just go out without reacting or reacting very little. So, that is blowout. Okay. Now, is that reasonable? Forget equations for a minute. Forget thinking about equations for a minute. You visualize this reactor in which you are sending high velocity fuel air mixture. So, the m dot is high now, and it has fuel, it has oxidizer. So, what I am saying is, if m dot is large, there is a possibility that the reaction will not take place. So, the reactants going in and the reactants going out, not products going out. Is this possible? What do you think?
In case they don't get sufficient time for the reaction.
Okay. So, the response is that in case the fuel and oxidizer do not get sufficient time to react, then they will just come out doing nothing. Okay. So, that is correct. Now, we can see this experimentally. We can build this spherical reactor and send fuel and oxidizer and keep on increasing the flow rate. We will see that at some stage the flow rates are so high that mass flow rate is so high that the reactants just come out without reacting. So, this can be checked experimentally. But we were talking more about solving equations, because we do not have the reactor and we cannot do the experiment here. But if you have these equations and if you try to solve them, in fact, that is what Turns has done in this example. He has solved those equations for this particular problem of 80 millimeter diameter reaction vessel by using what is known as a generalized Newton's method to solve all these 4 equations. Okay. So, if you solve equations, what you might see is that the product composition is the same as the product composition and temperature is the same as the reactant composition and temperature if m dot is too high. Okay. The other possibility is that sometimes, since these are nonlinear equations, coupled equations, you are trying to solve them together, it might not, the solution may not converge. If you are iterating, the solution may not converge, and some things will start happening if you have high value of m dot. Okay. So, you can check this out numerically, that there is a problem if m dot is high, there is no reaction, and if you can of course check this out experimentally. And what is the reason? As one of you pointed out, the problem is time. Okay. The problem is time. So, reaction requires certain amount of time, certain time, otherwise it cannot be complete, otherwise it cannot go to an acceptable level of completion. It might react a little bit, but that may be too small. So, we are actually talking about the available time versus the time required for chemical reaction. Okay. So, what is that available time? Again, I think last class you pointed out that there has to be a residence time. So, the residence time is more like this. So, this is density of the mixture, this is volume of the reactor divided by m dot. That should be a residence time, because this is got unit of kg, right. Density is kg per cubic meter, this is volume. So, this is meter cubed. So, this is kg, and you are sending at kg per second, m dot is kg per second. So, you get a time. So, this is time. Okay. So, this is residence time. Now, this residence time has to be sufficient for reaction to take place. So, if m dot is large, then the residence time comes down, then there is not enough time. So, they will go out unreacted. So, the residence time is more like a physical time. Okay, it depends on the flow rate, depends on the size of the vessel, depends on the density that you are getting, things like that. But there is also a chemical time. Chemical time is the time which is required for the reaction to go to some acceptable level of completion. Now, do we know something about chemical time? Yes. So, we looked at tau chemical, isn't it? I remember that we talked about primarily the tau chemical, that is the chemical reaction time scale for a bimolecular reaction, isn't it, for a bimolecular reaction. But of course, you could do that, and the book has those derivations for a unimolecular reaction and also for termolecular reaction, isn't it. the bimolecular reaction expression, if you probably remember that if A and B are reacting with one another to give you C and D, and if B is much greater than A, then we could make a simplification and we could actually show very easily that the chemical reaction time was inversely proportional to the reaction rate constant. So, there is the K bimolecular. So, tau chemical, which was the chemical time scale, was inversely proportional to the bimolecular reaction rate constant. Okay. So, that made a lot of sense, because if you have higher value of reaction rate constant, then the chemical time scale will come down. What was the chemical time scale? It was the time in which a certain fraction of A got consumed, isn't it? What was that fraction?
67%.
Yeah. So, we discussed all that. So, there is a chemical time scale. Now, if you change m dot, are you changing the chemical time scale? Yes or no? Now, why should the chemical time scale change if you change m dot? Chemical time scale was dependent more on K bimolecular, right? Of course, that was just one reaction that we are thinking of, that is A plus B giving you C plus T. Here, of course, there are multiple reactions which will take place. So, that was for an elementary reaction. We understood chemical time scale for an elementary reaction, but here it is like ethane going with oxidizer. So, lots of things will happen. Lots of radicals will get produced. Finally, CO will also get produced. We discussed hydrocarbon reaction mechanism. So, CO will get produced. Lots of things are going to happen. But in an overall scale, broadly, there is still some chemical time scale. Some good amount of time that you require for the reactions to complete, and that should not depend on m dot, isn't it? That should depend on some kind of a reaction rate, like a reaction rate constant, isn't it? So, for a bimolecular reaction, we said tau chemical is proportional to 1 over K bimolecular. So, here also the chemical reaction time scale must be inversely proportional to some kind of an overall reaction rate, isn't it? So, that will not change with m dot. What you are changing as you are increasing m dot is reducing the residence time for pretty much the same chemical time scale, and then reaction will not happen, and then you will get blowout. So, this is an important idea. So, if you have, let us say, gas turbine is something, conceptually something similar to this, because you are sending fuel and air mixture to the gas turbine and combustion takes place. Combustion products go out and then they will go and run the turbine. Okay. So, imagine what will happen if you try to push the fuel and oxidizer too fast through the turbine. Then they may not react, and if they do not react, then you do not get this hot gases which will go and run the turbine. So, you will get into trouble, isn't it? So, this is, even though we discussed a simplified model, of course, gas turbine is not well starred, in the sense that it is not uniform composition inside, and it is not the same reaction rate everywhere and things like that. But in a simplified perspective, we can understand that if you push the reactants too fast, maybe the rate of reaction will get affected, because the residence time is too small. Maybe reactions will not happen properly. Yeah.
Can we say like this, if the order of residence time is very less than chemical time scale, then reaction will not occur?
Yeah. So, we are saying that the other way of saying this is that, okay, you have a given reactor, you build that reactor thinking what is the largest possible rate of m dot that you would require for your process. You have some process, no? In the reactor, you are sending these reactants at a certain rate, because you want to achieve something. You want to achieve conversion from reactants to products. Okay, that is your objective. So, when you design the reactor, okay, so you think that, okay, this is the rate at which we need to convert. So, this is the maximum m dot that I need for processes downstream. Okay, this is the maximum m dot that I need. So, for this m dot, what is a good size for the reactor which gives an adequate residence time? So, the residence time is from here So, you make sure that the residence time is significantly larger than the expected chemical time. Okay. What I just now told you is valid even for other kinds of situations, for all combustion chambers where there is flow in, there is reactants flowing in and the products going out. Even if you think of a boiler design, you want to send the air and the pulverized coal. I am talking about coal combustion in a thermal power plant. You like to send the air and the coal at a certain rate, so that the coal particles get sufficient time to burn inside the combustion volume which is available in a boiler. In fact, later on in the semester we will learn that the boiler is so tall, okay, boilers are very tall, boilers are so tall because you want to give sufficient time for the reaction of coal to take place. So, coal particle, a 100 micron coal particle for example, it takes something like 1 second to burn. 1 second does not seem like a very large time, but it actually it translates to a long height. Okay. So, if the coal particle is moving at 20 meters per second into the boiler volume, and if it takes 1 second for the coal particle to burn, then you got what? What is the height? 20 meters. Okay. So, we will discuss this later, but I am not saying that that boiler is well-starred reactor, but in a sense the discussion that we had for the well-starred reactor is applicable for various kinds of combustors. So, that is all I am trying to say.
Equally applicable to even to the combustors of the aircraft engine?
Yeah, because an aircraft engine is also a gas turbine engine. So, the comment that I made about gas turbine, this being similar to a gas turbine engine, is applicable for aviation gas turbine also. Okay. So, that with that background, I think we can look at those curves which I started drawing yesterday. So, this is a set of curves. Now, can you take a look at this and try to interpret this? M dot, you increase m dot, you see that temperature will drop suddenly at a certain value of m dot. So, we understand this now, because at this value of m dot, the residence time has become so small, so the reaction does not take place, so the temperature actually drops. So, that is blowout. And similarly, if you give a small m dot, then the product concentration is actually quite high. Okay, it is almost equal to 1. So, this is 1 around here, this is 1, let us say, and if you increase m dot, temperature decreases, and you can also see that there is more oxygen and fuel in the product stream. What are these mass fractions? These mass fractions are in the product stream or inside the vessel. Okay, this is not the inlet mass fraction. Inlet in any case does not have any products. So, as you increase m dot, you see that Y products is coming down to some extent, and finally it drops abruptly, and Y O2 and Y fuel, they just try shooting up towards the end, okay, for this kind of value of m dot. So, it means that there is blowout happening around this range. Okay. So, this is blowout, this is blowout, and there is another plot in the book, and that also I will draw qualitatively, and that is a nice thing to see also. So, I am drawing this qualitatively, I am not placing numbers on this plot. So, I am not saying what this value is for example. Okay. So, for that you have to look up this figure 6.8 from the book, and this is equivalence ratio versus m dot at blowout. Let us see what does it mean. the last two plots that we saw, this is for a particular equivalence ratio. So, there is a certain fuel air equivalence ratio in the input mixture, and then maintaining that same equivalence ratio we are increasing the values of m dot. That is how we generated these plots. So, let us think about some other experiment where we change the equivalence ratio and let us say equivalence ratio of 1. At that equivalence ratio, we start with a small value of m dot, keep increasing the value of m dot, at some m dot blowout happens. So, we note that value, that for phi equal to 1, this is the m dot for which blowout happened. Then we choose phi equal to 0.9. Phi equal to 0.9 is lean or rich? Lean. So, phi equal to 0.9, again we do the same experiment, some small m dot, keep increasing m dot, at some m dot it fails. So, that is the blowout m dot. That way, for a range of equivalence ratios, you can find out what is the m dot at which blowout takes place. And if you do that, this is the kind of plot that you are going to get, and phi is around 1 here. Okay. And let us say this value is more like maybe 0.55 or something. Okay. So, what does it mean? It means that the m dot required to blow out a phi equal to 1 combustion process is larger than a linear mixture. Okay. So, it is kind of like this. So, as you go down this way, you are going down in equivalence ratio, you are making the mixture leaner. So, maybe this is 0.8 or something. Okay. So, at 0.8 your equivalence ratio, your m dot has come down. M dot is, this is m dot correspond to m dot blowout for phi equal to 1, and this is for less than that, and as you keep making it leaner, the value of m dot that is required for blowout actually comes down, right. Now, very quickly, we do not have much time left. Does this plot, the information that this is telling you, that linear mixtures have a tendency to get quickly blown out, or in other words, a stoichiometric mixture will be able to tolerate higher values of m dot. A stoichiometric mixture will be able to tolerate higher values of m dot, right. It will get blown out only for large values of m dot. Lean mixture gets blown out for much smaller value of m dot. Does this seem to make some kind of an intuitive sense? Do you think it's logical to expect? Do not think in terms of equations, because those equations, you can't solve those equations in your mind, right. Does this sound reasonable?
So, at the stoichiometric ratio, the probability of reacting the fuel with the air is much higher. In case of lean or very rich, that ratio is not.
Correct. So, the response here is that if you have a stoichiometric mixture, the flame is in fact stronger. Okay. And we know that to some extent. We had actually, you did this exercise with propane air, and you had done this equilibrium calculations, and you could actually see that T adiabatic corresponding to equilibrium for that propane air mixture, and it was more like this, and this was a function of equivalence ratio, and the maximum temperature corresponds to phi value of 1.05 or so. Okay. So, if you give the right amount, the chemically correct amount of air for the fuel concentration that you have, you get higher temperatures, which means that the reaction is good and things like that. So, it is a strong flame. So, if it is a strong flame, it is not going to blow out that easily. Okay. So, you need a higher value of m dot. If you do a lean mixture, it is very delicate, because it has got too much air, too little fuel, the reaction is weak, the adiabatic flame temperature is low, so it is a weak flame. Okay. So, I am using words like strong and weak in kind of a simplistic sense, but I think you get a sense of what I am trying to say. So, if you have a lean mixture 0.55 equivalence ratio, then it gets blown off quite easily. If you go much below that, much below the bottom of this curve here, I mean there is no question of blown out, because it will probably not even give you a flame. Okay. All right. Now, is this important? This is important because in lots of combustion systems, including gas turbines, the trend is to burn lean. So, there is lean premixed combustion that is used in gas turbines nowadays to keep the emissions low. Okay. To keep the emissions low, that we cannot discuss now, especially because we just have 1 minute left. But lean premixed combustion is being used with modern combustion technology. Okay. But you see the problem. But okay, it's nice, maybe it will keep the pollutants less, but lean premixed combustion means your system is actually vulnerable. There are greater chances of blowout. So, you have to be careful about the m dot that you are pushing into the combustion chamber, correct? Okay, I think that's it. So, we will stop here, and in the next class we will start going towards discussion of flames. So, we have completed discussion on constant pressure reactor, constant volume reactor and well starred reactor. I will encourage you to read about plug flow reactor on your own. We will not be discussing that in class, okay, for the sake of for the interest of time, because we want to go to more flame related discussion after this. Okay. So, we will stop here. Thank you.